Everything you see right now, your hands, this screen, the room around you, might not be three-dimensional at all. It might be a projection, a hologram, flat information on a distant boundary that only looks like it has depth. I know this sounds like science fiction, like something from the Matrix. But I'm one of the physicists who proved it might be true. My name is Leonard Susskind, and in 1994, I published a paper that turned our understanding of reality upside down. Let me tell you how I figured it out. Let me take you back to the early 1990s. I was at Stanford teaching physics the way we'd always taught it. Space has three dimensions: up, down, left, right, forward, backward. That's how we experience the world, right? You can walk forward, you can jump up, you can move sideways. Three independent directions. Three dimensions of space. And if you want to describe everything happening in a room, every particle, every field, every quantum state, you need information proportional to the volume of that room. Makes perfect sense. A bigger room has more stuff, so it needs more information to describe it. That's what every physics textbook said. That's what I believed. Black holes were the weird exception. In the 1970s, Jacob Bekenstein and Stephen Hawking had discovered something strange about black hole entropy. Entropy measures information, how many bits you need to describe a system. For normal objects, entropy is proportional to volume. But for black holes, it's proportional to RE, the surface area of the event horizon. At first, physicists thought this was just a quirk of black holes, some weird gravitational effect that only matters in the most extreme conditions. It didn't seem to have anything to do with everyday physics. It was interesting, sure, but it was an isolated result. I remember teaching thermodynamics and mentioning this as a curiosity. Isn't that weird? I tell my students, black holes don't follow the normal rules. But I didn't think it was revolutionary. None of us did. Meanwhile, Gerard Hooft in the Netherlands was thinking about the same problem from a different angle. Gerard is brilliant, one of the sharpest minds in physics. He'd been worrying about information and black holes since the early 1980s. And in 1993, he published a paper with an absolutely crazy idea. Gerard suggested that maybe the black hole result wasn't an exception. Maybe it was a RAL-E. Maybe the maximum information in ANY region of space, not just black holes, but any region, is limited by its surface area, not its volume. When I first read Gerard's paper, I thought he'd gone too far. It was one thing to say black holes are weird. It's another thing entirely to say that EVRITIG is like a black hole in this respect. That seemed impossible. But I couldn't stop thinking about it. Here's what kept bothering me. I'd been working on black hole complementarity, my response to Stephen Hawking's claim that black holes destroy information. I'd argued that information survives, that it gets encoded on the event horizon. The horizon acts like a boundary that records everything that falls in. But if that's true, if the horizon is like a giant hard drive storing all the information, then there's something deeply strange going on. The information about what's inside the black hole is somehow fully contained on its SU-RFACE. The two-dimensional horizon contains all the information about the three-dimensional interior. That's when Gerard's idea started to make sense to me. I was sitting in my office at Stanford one afternoon in late 1993, staring at my equations about black hole horizons. And I started playing with a thought experiment. What if you could surround AN region of space with an imaginary surface? Not just a black hole, any region, your room, the Earth. A galaxy. The question is, how much information can that region contain? Now, here's where it gets weird. Imagine you start adding more and more stuff to that region. More particles, more energy, more matter. You keep packing it in, making it denser and denser. What happens eventually? Eventually, you make a black hole. You can't avoid it. If you compress enough mass into a small enough space, gravity takes over and you get a black hole. That's basic general relativity. And once you have a black hole, Bekenstein and Hawking told us that its entropy, its information content, is proportional to the area of its horizon, not the volume. The area, this means the maximum information you can stuff into a region is limited by the area of the boundary around that region, not the volume inside. If you try to cram in more information than the area allows, you just make a bigger black hole with a bigger horizon. The area limit still holds. I jumped out of my chair when I realized this. This wasn't just about black holes. This was a fundamental limit on information in space. Any space, all space. Let me give you an analogy. Imagine you're trying to store data in a room. Normally, you'd think you could build shelves throughout the whole room. Use the entire volume. More volume, more storage. But what if there's a physical law that says, no matter how clever you are, the maximum data you can store is actually limited by the walls? Not the space between the walls themselves. That's what the holographic principle says. The walls, the boundary, are what matter. The three-dimensional interior is somehow encoded on the two-dimensional boundary. It's like a hologram. You know those 3D images you see on credit cards? They look three-dimensional, but all the information is actually stored on a flat surface. The 3D image is a projection. What if our universe works the same way? I called Gerard immediately. He was in Utrecht. I said, Gerard, I think you're right about this boundary idea, but it's even bigger than you said. It's not just a cute result about black holes. It's a fundamental principle of nature. There was a pause, and then he said something I'll never forget. Lunny, I think we're both crazy, but we're the same kind of crazy. Over the next few months, I worked out the details. The key insight is what I call the holographic principle, the maximum entropy. The maximum information in any region of space is proportional to the area of its boundary, measured in Planck units. Let me break that down. A Planck unit is incredibly tiny, about 1033 centimeters. That's the smallest meaningful length in physics, where quantum gravity effects become important. The holographic principle says you get 1 unit of information, 1 bit, for every square Planck area on the boundary. Now, this sounds like it gives you less information than you'd expect from three-dimensional space. And you'd be right. For a region the size of your room, the holographic limit is vastly less than the amount of information you'd expect if every point in the volume could store data independently. So why don't we notice this limit in everyday life? Because we're nowhere close to reaching it. To actually saturate the holographic bound, to pack in the maximum possible information, you'd need to compress matter to incredible densities. Densities where quantum gravity matters. Densities where you're forming black holes. In our everyday world, we're operating at information densities millions and millions of times below the holographic limit. We have plenty of room. The bound is there, but we never hit it. The important thing is that the bound exists. There's a maximum, and that maximum is determined by area, not volume. Here's another way to think about it. Imagine the universe as a giant computer program running a simulation. If you're coding this simulation, how much memory do you need? You might think you need memory proportional to the number of points in space, the volume. But the holographic principle says no. You only need memory proportional to the boundary of the region you're simulating, the surface. The interior, all 3 dimensions of it, can be reconstructed from the information on the boundary. The 3D world is a projection from 2D data. Now, I need to be honest with you about something. When I first presented this at conferences, a lot of physicists thought I was out of my mind. Abe Witten sat in the front row at one talk, and he had this look on his face like he was trying to decide if I was brilliant or completely insane. Maybe both. The holographic principle sounds impossible because it violates our everyday intuition about space. We feel like we live in 3 dimensions. We can move in 3 independent directions. How can that be an illusion? But here's the thing about physics, your intuition is calibrated by everyday experience, and everyday experience doesn't include black holes or quantum gravity. At the extremes, very small scales, very high densities, the universe doesn't work the way your intuition expects. Think about it this way. You're reading this on a screen right now. That screen is 2-dimensional, it's flat. But it displays 3-dimensional images. Video games, movies, photos, they all look 3D, but they're encoded in 2D. Your brain reconstructs the depth. The holographic principle says the universe might work the same way. We experience 3 dimensions, but the fundamental information, the actual code of reality, might be written on a distant 2-dimensional boundary. Everything we see, everything we are, might be a projection from that boundary. Where's this boundary? That's a great question, and honestly, we don't have a complete answer. For black holes, it's clear the boundary is the event horizon. But for the universe as a whole, that's still an open question. Some physicists think it might be at the edge of the observable universe, at the cosmological horizon. Others think it might be a more abstract mathematical boundary. We're still figuring it out, but the principle holds. Maximum information equals boundary area, not interior volume. I published the paper in 1994. The world is a hologram? It's become my most cited paper, over 400 or 500 citations at this point. It's the work I'm probably best known for, at least in the physics community. But here's what really made the holographic principle concrete, Joan Maldacena's discovery in 1997. Joan, who's probably the smartest person I know, proved something called ADS CFT correspondence. He showed that a specific type of gravitational theory in a space called anti-de Sitter space is mathematically equivalent to a quantum field theory on the boundary of that space. This wasn't just a vague principle anymore. This was a precise mathematical duality. The physics in the interior, including gravity, could be completely described by a theory on the boundary with one fewer dimension. No gravity, just quantum fields. ADS CFT made the holographic principle concrete. It gave us a working example, and it launched an entire research program that thousands of physicists are still working on today. The holographic principle changed how physicists think about space, information, and quantum gravity. It connected ideas that seemed completely separate: black hole physics, string theory, quantum information. Suddenly, they were all part of the same story. Gerard Hooft and I had arrived at this idea independently around the same time. We were both thinking about information and black holes, and we both realized the boundary is what matters. It wasn't a competition. We were thrilled that two people had stumbled on the same wild idea from different angles. That's how you know you're onto something real in physics. The impact on string theory was huge. Before the holographic principle, string theorists were trying to understand how strings behave in curved space-time. After holography, they realized you might not need to work in the bulk, the interior, at all. You could describe everything from the boundary. This led to an explosion of research. People started looking for holographic descriptions of different spaces. Black hole thermodynamics made more sense. Entropy wasn't some weird exception. It was exactly what you'd expect from holography. The horizon area is literally the amount of information measured in Planck units. But here's where I need to be straight with you. Some physicists took the holographic principle and ran wild with it. They started claiming it means we literally live in a simulation, that we're characters in some cosmic computer program. That's not what I'm saying at all. The holographic principle is a statement about information and physics. It says the maximum information in a region is bounded by its surface area. It says a 3D gravitational theory can be mathematically equivalent to a 2D quantum theory. It does now say that someone is running a simulation on a computer somewhere. Could our universe be a hologram? In the technical sense that the physics in our 3D space might be described by a theory on a 2D boundary, yes, maybe. In the pop culture sense that we're in the matrix, no, that's not what this means. Physics is about finding mathematical descriptions of nature. The holographic principle is one such description. It's powerful, it's elegant, it's probably true in some form. But it's not magic, it's not mysticism, it's physics. The other major development came from my own work on black hole complementarity. Remember, I'd been arguing that information survives black holes. The holographic principle supported this. If all the information is on the horizon, then when the black hole evaporates and the horizon shrinks away, the information can escape with the Hawking radiation. It's not destroyed, it's preserved on the boundary the whole time. This was crucial for my debate with Stephen Hawking. Stephen had argued that information is destroyed. The holographic principle gave me a framework for understanding how information survives. It's encoded on the horizon, and it can be recovered from the radiation. No information is lost. Now, Stephen didn't concede immediately. The black hole war went on for another 10 years after I published the holographic principle, but this was a major piece of evidence on my side, and when Joan Maldacena proved ADS CFT in 1997, that was even stronger evidence. We had a concrete mathematical example of holography working. Today, the holographic principle is mainstream physics. It's taught in graduate courses. It's the basis for huge research programs. Young physicists grow up with it. They don't find it strange the way my generation did. To them, it's just how quantum gravity works. But I'll tell you, even after 30 years, it still blows my mind sometimes. The idea that three-dimensional space might be emergent, that it's not fundamental, but rather a projection from something more basic, that's radical. That changes everything. So where does the holographic principle lead? What are we still working on? Let me connect some dots for you. First, there's the question of our actual universe. Joan Maldacena's ADS CFT result is beautiful, but it applies to anti-de Sitter space, a space with negative curvature. Our universe has positive curvature. It's de Sitter space, not anti-de Sitter. We're accelerating, expanding faster and faster. Does holography work in de Sitter space? That's the problem I've been obsessed with for the past 5 years. And honestly, it's way harder than the ADS case. There's even a no-go theorem, proven by me and some collaborators, that says you can't have perfect de Sitter symmetry and finite entropy at the same time. Something has to give. We're still working on it. Edgar Shagolian, Adil Rahman, and others in my group are trying to crack this. But we don't have the answer yet. This might be the problem that outlives me. I'm 86 years old, the clock is ticking, but that's okay. That's how physics works. You solve some problems and you leave others for the next generation. Second, there's the connection to quantum information and complexity. My later work on complexity, the idea that computational complexity keeps growing inside black holes, is deeply connected to holography. The complexity is measuring something about the geometry of space-time. It's another way that information and geometry are linked. This ties back to EREPR, the idea Juan Maldacena and I developed that wormholes are the same thing as quantum entanglement. If entanglement creates geometry and geometry is holographic, then entanglement must be encoded on boundaries too. Everything connects. Third, there's the fundamental question, what is space? If space is emergent, if it's a projection from something more fundamental, then what's the underlying reality? What's the boundary actually made of? What are the fundamental degrees of freedom? We don't know. But here's what I suspect. I think space, three-dimensional space that we walk around in, is not fundamental. It's an emergent phenomenon like temperature or pressure. Temperature isn't a fundamental property. It's the average motion of particles. Pressure isn't fundamental. It's the momentum transfer of collisions. I think space is the same way. It emerges from something more basic. Maybe it's quantum entanglement. Maybe it's information. Maybe it's some mathematical structure we haven't discovered yet. But I'd bet my house that 100 years from now, physics textbooks will describe space as emergent, not fundamental. And that's the real revolution. Not that we live in a simulation. Not that reality is fake. But that the three dimensions we experience every day are emergent properties of a deeper reality. That's profound. That changes how we think about everything. This connects to the string theory landscape I worked on in the 2000s. If there are 10, 500 possible universes, my most controversial idea, then maybe each one corresponds to a different holographic boundary. A different way of encoding information. We're in the universe where the holographic projection produces stars, galaxies, planets, and us. It all fits together. Holography, quantum information, entanglement, complexity string theory. They're all pieces of the same puzzle. We don't have the full picture yet, but we're getting there. After 50 years of doing physics, here's what I've learned. The universe is always stranger than we imagine. Always. Every time we think we understand something fundamental, we discover a deeper layer. 300 years ago, Newton thought space was absolute, fixed, unchanging. Einstein showed that space curves and bends with gravity. Now we're realizing space might not even be fundamental. It might be an emergent illusion. That's the beauty of physics. We keep peeling back layers. And each layer reveals something more surprising than the last. The holographic principle is one of those layers. It's not the final answer. There are deeper questions still. But it's a step toward understanding what reality actually is. My father used to tell me, "You ain't gonna be no engineer. You're gonna be Einstein." He was a plumber from the Bronx. He never got past 8th grade. But he understood something important, that asking big questions about the universe is what makes us human. I've spent my whole life asking, what is space? What is information? What is reality? The holographic principle is my best answer so far. The universe might be a projection from a distant boundary. 3 dimensions might emerge from 2. That's weird. That's beautiful. And it might be true. I don't know if we'll figure out all the details in my lifetime. I'm 86 years old. I've got maybe 10 good years left, if I'm lucky. But the next generation will keep pushing. They'll answer questions I can't even formulate yet. That's how physics works. We stand on each other's shoulders. Gerard stood on Bekenstein and Hawking's shoulders. I stood on Gerard's shoulders. Young physicists today stand on mine. And someday, someone will stand on their shoulders and see even further. That's the whole ball game.